So next up, I'm really excited to introduce our speaker, Dr. Signe Redfield. She is the director of the Naval Research Laboratory's Laboratory for Autonomous Systems Research. She's the chair of the IEEE Guidelines for Verification of Autonomous Systems Standard Development Working Group, a founding co-chair of the IEEE Robotics and Automation Society's Technical Committee on Verification of Autonomous Systems, and the secretary for the IEEE Robot Task Representation Ontology Standard Development Working Group. She's been working in verification standardization and fault management of autonomous systems since 2014 and is currently co-editing a book on verification of autonomous systems. She's worked on space and maritime autonomous systems, developed behaviors and decision algorithms controlling operation of single components, individual agents, and heterogeneous teams in development and assessment of the simplest reactive systems all the way to AI models. So with that, Signe, take it away, please.
Okay, thanks. Well, thank you very much for the opportunity to present. I don't know whether you're more keen on the equations or the videos, but I am sorry to say that this talk is very boring and has neither one. What I'm going to be talking about are the things that we've been assembling into this new standard, which is a best practices guide for verification of autonomous systems. Now, these slides were developed for another talk, but I do hope you'll find them helpful. The content is the result of many people's work on the standards development group, and I encourage you to join us. So verification is fundamentally about how you ensure the safety, security, and functionality of your system before you deploy it. And before I go any further, I just want to add a note that when I'm talking about safety in this talk, I mean not just the safety of the system, but the safety of the environment in which it operates, the safety of bystanders, the safety of objects it's intended to interact with. Not just does it break, but does it break the egg? Does it break the skin? Does it attack the cat? And so it's, our guide really has goals that are based in this external, not design-centric, but evaluation-centric approach to autonomy. Our main goals are to enable users to develop a customized process that they can use to verify their autonomous system based on what they have available to do that, to document best practices as they're currently understood in the community, and to document common pitfalls, which is really big in autonomy. We're currently about halfway through developing the guide. It's definitely a work in progress. But we have started to pull the various threads together, and this talk is kind of about what we know so far. The scope of the guide is specifically autonomous systems. They may be mobile or immobile, virtual or physically embodied, reactive or learning, but they make their own decisions. They're not automated or pre-programmed or teleoperated. It also focuses specifically on verification, on ensuring that a designed system provides the specified functionality, not on checking whether that specified functionality actually meets user needs. And the guide is aimed jointly at people in the industry test and evaluation community and the certification and licensure professionals that lack experience with autonomous systems, and at autonomy developers that lack experience with deployment to operational situations. So we have the context set. On to the details. So if you need a safe, reliable system, especially from this evaluation perspective, you need to spend some serious time thinking about the context that you're working in. You need to think not just about whether it's reliable and safe, but about how you're going to prove that it's reliable and safe. So what tools do you have? What's appropriate for your problem? Do you have simulators or models or test ranges? What expertise do you have? If you have mathematicians, logicians, formal analysis experts, controls experts, maybe you have component experts or environmental experts or task experts. You're going to need everybody to answer these questions. You need to know how much time and money you're willing to allocate, because the verification typically comes at the end and typically comes as a rude shock in terms of how much it costs. And do you have the authority to define or accept or reject specifications? Because often people who are unfamiliar with autonomous systems will produce specification sets that are really not helpful at all. And you need to know when the verification process will be active. Are you mainly focusing on design and development? Are you doing formal analysis of the controls? Are you engaging after the design is complete and you have a black box system and you don't actually know what's inside it and you have to guess and develop tests? Or are you working at the deployment stage where it's already been built, but it has an AI model and you have to continually verify it as it runs? This is critically important for autonomy, since the metrics driving the decisions are critically intertwined with both the effective testing regimes and the system performance and failures. All right. There we go. So we're looking at a 4-step process. So first you take this inventory. You have to know what you have. Then you design your verification process, you gather evidence, you determine whether the requirements are met. So step 1 is done when you have all this information, which means it's possible to figure out what processes apply to your situation. The second step, define verification process, that's the one where you discover that your tools are inadequate and you can't complete the job within your time and budget. It is possible to reduce risk and increase confidence, but it's often a rude shock to the systems engineers when they discover how little we know about autonomy. I guess the key thing to remember when you are in this verification bubble is that the goal isn't, is it safe, but is it safe enough? Not is it reliable, but is it reliable enough? And this last step, determining whether the system meets its requirements. That drives a lot of problems with specification and requirements, and we're going to get to that in a couple of minutes. All right, so what do best practices and verification processes for autonomous systems look like? Well, fundamentally, you need to use all the tools available to gather enough information about the system. But each process centers different information, defines a different relationship between the tools you have and how you assemble the information you gather. So we have an analytic approach where the core evidence provided is in the form of mathematical guarantees about when and what properties hold. This is very much like the talks we've heard today, where you build the math into the controller and then you have guarantees about how well it's going to work and when it's going to be safe. The other evidence buttresses and supports these assertions. So if you have a robot that has one of your guaranteed controllers, you have to work through and figure out what the assumptions are that you're making about the environment, because that will drive the tests that you have to do later. In the simulation approach, the simulation results are the primary evidence that the system will do its job and respond to faults correctly. And the analytical tools are used to block off regions of the simulation space that don't need to be explored. And physical testing is used to ground truth the simulation, proving that its results are trustworthy and valid. In the physical approach, the results of the physical testing are the primary evidence that the system will perform correctly, and simulation and analytic results fill in the gaps where you really can't explore the performance space with physical testing. The manual approach is the most traditional. You build a, as bulletproof as possible, set of requirements. Once you're satisfied that the requirements actually describe what you need, all you have to do is demonstrate that the system meets the requirements and you're done, except that's very challenging. And even developing the requirements is a very time-consuming, difficult, and expensive process, even for a simple autonomous behavior that's only responsible for 1 or 2 decisions. But this approach can be very effective if you throw sufficient resources at it. So the space community in general operates this way, and they throw a ton of resources at it, and it works. When different elements of a system require reliance on different types of evidence, the combination approach is the best practice. And there is one more approach. It's not a best practice. It's just how autonomous system verification is commonly done, which is you try to find the combination of evidence that will maximize the requirements you're able to verify and minimize the risk, while simultaneously trying to keep the cost and time down to the point where it's tractable. So processes. You look at the tools you have, you look at the expertise you have, and you say, okay, I'm going to take this approach to how I'm going to solve this problem. So you've selected a process structure and you know what tools you have. So let's take a minute to talk about the specification. In most cases, we have extremely poor and inadequate specifications for autonomous behavior. It's essential for autonomous behavior designers to be in the room when a specification for an autonomous behavior is being developed, because they provide feedback about what information they actually need, and they're able to stop the systems engineers before they start redesigning behaviors that were originally created in the 1980s. But it's not enough to include the behavior designers. You also have to include the task specialists, because it's the interaction between those two groups that define the actual requirements on the autonomous behavior itself. So if we look at a simple avoidance behavior, say we have an arm, like a human arm, and we want to say that it shouldn't hit things when it moves. Non-autonomy specialists will follow a process like the one in the top row. You start with a requirement, you develop an initial common sense requirement, you add a bunch of exceptions as you explore the world and discover that it's really not actually covering the problem well. And it gets too complicated and everybody gets really uncomfortable with it. And you step back and you redefine from a new perspective. You go from shall not contact objects to shall not damage itself or its surroundings. And the same thing happens again, and you loop back. And either you end up with requirements that are useless to the designers, or you end up with the systems engineers going, this is untestable, we give up, we're not having a requirement for autonomy, we're going to constrain the system in other ways, so avoidance is implicit. This is very unhelpful. When you add autonomy designers to the room, you can start explaining what information will actually help them design the behavior. And that will produce much more testable requirements for the one, like the ones on the bottom. Things that focus on the goals, the criteria for allowed and disallowed actions. What happens with the fault conditions and what kind of desired responses you have. It lets you outline where the edges of the behavior you're trying to design are. So it is possible to develop good autonomous behavior requirements, but they rely on capturing the goals and the metrics rather than the specific sequence of actions to be undertaken. The operating context, the constraints, the expectations all have to be clearly spelled out. And the requirements need to differentiate between faults that are handled as part of the behavior design, faults that have special responses defined that are part of the fault response rather than the task level behavior design, and faults which can't be avoided or mitigated and have to be excluded via operating constraints. And any of these faults can take the form of trade-offs within the software design or in the form of invalid environmental assumptions. So we have, let's just assume we've done this, we have specifications. From here on in, we're going to be talking about the specific techniques that people use to prove that their system is safe, secure, and reliable. And before we go any further, I need to call out a little bit of terminology because there are 4 different kinds of models that I'm going to be referring to, and it gets confusing if you start mixing them. So formal models are abstract. They're logical or mathematical representations. They can represent requirements, design, operational context, desired properties. What they do is they enable logical checking that the properties hold. They enable identification of failure modes. They enable you to analyze the system mathematically rather than via brute force or simulation. System and process models are detailed or abstract representations of the system or its behavior, whatever is being used to accomplish the task, whatever is being tested. Environment models are detailed or abstract representations of the environment within which that system or behavior operates. And AI models, of course, aren't models of, they are the actual component under test. So once you know what the system is able to do, or supposed to do, once you know the context within which it's supposed to operate, the constraints under which it is and is not supposed to make decisions, then you can start actually verifying your system's safety, security, and reliability. Now we're going to start with formal methods, mathematical, logical, and analytical tools. Basically, they provide guarantees. They enable you to include and exclude particular operating states. They identify design flaws and when requirements have been violated. Most importantly, they apply across all stages of the development lifecycle. As long as the built system matches the modeled system and your assumptions hold, everything is okay. You can use them both to verify and to construct controllers. Our focus is mainly on the verification side rather than on the controller construction. Now, developing these models and methods typically requires a significant investment because you have to understand the properties that need to be verified, what you can eliminate from the model and what you need, and what assumptions you need to identify. Capturing and expressing these assumptions is a big part of the investment in developing these formal models of the system. In the analytical verification approach, simulation of the system and its environment is typically used to determine whether those assumptions are valid or not. So simulations let us provide performance assessment for system models in enormous numbers of environmental and task contexts. Our guide covers several types of simulations: physical simulation, where the behavior is tested in an analogous platform and environment; hardware in the loop simulations, where the behavior is tested in a partially simulated environment; and pure simulation, where the platform and the environment are completely virtual. Now, when you work with autonomous systems, your simulations, in addition to the environmental models and simulations of the system under test, also need support for dynamic environmental processes and autonomous agents in the environment, which makes them very complex. The DARPA Sub-T Challenge simulation is an excellent example of a simulation that's originally constructed and designed to improve system performance and to help the competitors understand the context their systems will be operating in, but that still manages to illustrate the necessary properties of a verification simulation. Best practices for simulations for verification: you need to balance fidelity, cost, and time. You should automate wherever possible. You should focus the scenarios that you want to evaluate in your simulation on the scenarios that you can only run in simulation, because you can't constrain the world to create that particular environment. And you have to buttress your simulation results with physical testing. Now, of course, once you have the simulation capability, the performance space of the system and its environment is too large. And we lack theoretical tools that will enable us to predict autonomous system performance generally. So we need intelligent ways to identify and explore the part of the performance space that's interesting and relevant to simulate. And this is where sampling-based testing comes in. So our guide is covering deterministic methods, regression testing, parameterized simulations, stochastic methods. Tools like the Range Adversarial Planning Tool, or RAPT, shown here, enable automated simulations to home in on regions of the performance space where changes in the system parameters or environmental configuration trigger performance changes. So when you embed your Avoid controller into a physical system that is attempting to perform a complex task, this tool will help you identify where you're going to run into trouble. You'd use it when you need to characterize a black box system whose insides you don't know, when your white box system is too complicated for exhaustive evaluation, when you need to down select from a large set of tests so that you actually can do the physical tests that you can afford, and when you need to discover false failure cases and emergent behavior, but with the caveat that your simulation has to actually incorporate the information that allows you to discover those faults and failure cases and emergent behavior. In general, you want to start small and work up to more complex scenarios and save the most relevant data, if not all the data. But simulations and sampling test scenarios isn't going to be sufficient to ensure that we accurately capture system performance. We also need at least some hardware testing. So why do we include hardware testing when we're verifying rather than validating? We need hardware testing to ground truth the simulation and analysis results, to identify cases where problems occur in simulation that can't occur in the physical world, and cases where problems occur in the physical world that don't occur in simulation, to ensure that our assumptions hold and understand how and when they fail. So the guide covers developmental testing in controlled environments to build confidence that the specifications are met, and operational testing in an uncontrolled operational environment to ensure the system retains the properties and function we established during development. So Waymo runs extensive simulations to assess likely behavior, but they also have closed test tracks where they perform significant hardware testing, both to ensure the validity of their simulations and to identify edge cases based on details that aren't captured in the simulations. All right, and finally we get to runtime verification. So we're not at a point where we'll be able to adequately verify all the parts of an autonomous system. Controls is moving ahead very fast and is doing really good work. But if you look at AI perception algorithms, if you look at all these other tools that we have, we don't know how to verify individual pieces unless we design them to be verified. And we don't know how to verify the integrated system in a way that the certification agents are likely to accept. And especially, we can't verify it based on all the scenarios it's going to run into. So we add a monitor to the system to ensure it doesn't go outside the boundaries we've defined. And we put all the things we can't verify inside that box. So runtime verification provides assurance that the behavior in the system box will remain in those expected and desired bounds of operation. It's usually implemented via formal checking for property violations, but it could also be implemented as monitoring of the input data to see whether it's inside the scenarios that the perception algorithm was trained on. Best practices for this are to keep the monitor simple with clearly defined automated responsibilities, because the last thing you want is a situation where your monitor is now more complex autonomy than the stuff inside the box. Now, we're also working on assurance case construction and licensing and certification implications, but we're still working through those concepts and details, and I don't have slides on them yet. So it may not be possible to verify an autonomous system to the degree of risk that we require for other things, but it is possible to reduce the risk associated with using an autonomous system. If you have the right combination of tools, expertise, and resources, you can establish the limits on the operating environment. You build your controller for a flat space, and you know that it is only going to have to work in a flat space. If the system is at the right stage of development for the tools you have available, tools that you use designing a controller are not necessarily going to be helpful if you have to apply them at the test and evaluation stage before you deploy. You can do this if you have enough insight into the system design and operation, if you understand precisely what the system is supposed to do, and I cannot emphasize how much it is important to know precisely what the system is supposed to do, and the circumstances under which you do not know what it is supposed to do, where the desired action is ambiguous. What these constraints buy you is a starting point. You still have to design a process that gathers the information you need. You still need to figure out what information you need, but the constraints put you in a place from which you can build a process that will actually generate the evidence that you need about whether the autonomous system will actually operate as intended. And before I finish, it's a big list of people. These are the people who have contributed a lot or contributed recently. And I thank them all because none of these slides would be here without them. And that's it. Thank you.